Picture this. You're standing in a smoky medieval foundry, sweat dripping down your face as molten bronze glows like liquid fire just 3 feet away. The air tastes like charcoal and metal, and every breath makes your lungs feel like they're getting a chemistry lesson. One wrong move with that 2,000-degree soup, and you're not just having a bad day, you're having your last day. But if you get it right, if every measurement and timing is perfect, you're about to create something that could change the course of history. Welcome to the world of cannon casting, where art meets warfare and bronze becomes the ultimate game changer. Most people think cannons just appeared one day, fully formed and ready to knock down castle walls. Wrong. These metal monsters were the result of centuries of trial, error, and more than a few spectacular explosions that probably sent foundry workers running faster than they'd ever run before. The process of turning raw copper and tin into a weapon that could hurl a 50-pound stone ball over half a mile wasn't just impressive, it was borderline magical for its time. Here's something that'll blow your mind. Creating a single cannon required the same amount of bronze as making 200 church bells. Think about that for a second. Churches back then were basically showing off their wealth with these massive bronze bells. And here come the weapon makers saying, "Hold my ale, watch this." They took that same precious metal and turned it into something that could punch holes through 3-foot-thick stone walls like they were made of paper. The whole process started with what foundry workers called the Great Weighing. This wasn't your kitchen scale situation. We're talking about carefully measuring out hundreds of pounds of copper and tin with the precision of a master chef making his grandmother's secret recipe. Get the ratio wrong by even a few percentage points, and your cannon might explode the first time someone tried to fire it. No pressure whatsoever. The standard recipe called for about 90% copper and 10% tin, creating what metallurgists called gun metal or bell metal. But here's where things get interesting. Different foundries had their own secret tweaks to this formula. Some added a pinch of lead for easier casting. Others swore by a tiny amount of zinc. These weren't random experiments either. Master founders guarded their alloy recipes like state secrets, passing them down through generations of apprentices who probably had to swear blood oaths not to spill the beans. One fascinating detail most people don't know is that the copper used in these cannons often came from mines hundreds of miles away. We're talking about medieval supply chains that would make modern logistics managers weep with envy. Copper from Cornwall, tin from Bohemia, charcoal from specific forests known for producing the right kind of wood. It was like assembling ingredients for the world's most expensive and dangerous recipe. The charcoal situation deserves special mention because it wasn't just any old burnt wood. Cannon founders needed charcoal made from specific trees, aged just right, and produced using techniques that hadn't changed since Roman times. Oak was the gold standard, but beech and birch worked too. The charcoal had to burn hot enough to melt bronze, that's over 1,800 degrees Fahrenheit, while also burning clean enough not to contaminate the metal. Getting bad charcoal was like trying to cook a gourmet meal over a garbage fire. But even perfect ingredients meant nothing without the right furnace setup. These weren't your backyard barbecue pits. Medieval cannon furnaces were engineering marvels that could maintain temperatures hot enough to melt copper while being fed by bellows operated by teams of workers. The bellows alone were massive leather contraptions that required multiple people to operate, pumping air into the furnace with a rhythm that had to be maintained for hours at a time. The melting process itself was pure theatre. First came the copper, broken into chunks and fed into the crucible like feeding a very hungry, very hot dragon. The metal would slowly turn from solid chunks into a glowing orange liquid that looked like molten lava. Then came the tricky part, adding the tin at exactly the right moment and temperature. Too early, and the tin would burn off. Too late, and it wouldn't mix properly. The master founder had to judge this by eye, watching the color of the molten metal and listening to the sound it made as it bubbled and moved. Here's something that would make modern safety inspectors faint. Founders tested the alloy by dipping a cold iron rod into the molten bronze and examining how it cooled. They could tell if the mixture was right by the color, texture, and even the smell of the cooling metal. It was like wine tasting, except the wine was liquid metal hot enough to vaporize your face if you got too close. The skimming process was equally dangerous and crucial. As the bronze melted, impurities would rise to the surface like scum on a pot of soup. Workers had to carefully skim this slag off using long iron ladles, removing every bit of contamination while trying not to splash molten metal on themselves or anyone else. The slag itself was actually valuable. It could be reprocessed to recover any good metal that got caught up in the waste. Temperature control was the real art form here. Too hot, and the bronze would absorb gases from the air, making it weak and porous. Too cool, and it wouldn't flow properly into the mold, creating weak spots or incomplete sections. Master founders developed an almost supernatural ability to judge temperature by the color of the metal and the way flames behaved around the crucible. They were like human thermometers, except their accuracy meant the difference between a working cannon and a very expensive paperweight. The timing had to be perfect, because once the bronze reached the right temperature and composition, you had maybe a 20-minute window to pour it before it started cooling and becoming unusable. This created incredible pressure on the entire Foundry team. Everyone had to know their role perfectly, because there were no do-overs. Mess up the pour, and you just wasted weeks of preparation and enough bronze to buy a small village. What made this even more challenging was that the mold had to be ready at exactly the same moment the bronze was perfect for pouring. This meant coordinating two completely separate processes, alloy preparation and mold construction, with split-second timing. It was like conducting an orchestra where every musician was handling something that could kill them if they made a mistake. The economics of the whole operation were staggering. A single cannon casting could consume as much bronze as a wealthy merchant made in a year. The charcoal alone cost more than most people's annual wages. Add in the specialized labor, the weeks of preparation time, and the risk of total failure, and you're looking at an investment that could bankrupt smaller kingdoms. This is exactly why cannon production became centralized under royal control. Only princes and kings had the resources to sustain this level of expensive, high-risk manufacturing. But all this careful preparation was just the beginning. Once you had your perfect bronze alloy bubbling away at exactly the right temperature, the real challenge began, creating a mold that could handle 2,000 pounds of liquid metal without falling apart, exploding, or producing a cannon that would kill its own crew the first time they tried to fire it. The mold-making process was where medieval foundry workers truly earned their reputation as half-wizard, half-lunatic. You couldn't just dig a hole in the ground and hope for the best, though apparently some early cannon makers tried exactly that, with results that probably made their insurance adjusters weep. Creating a mold that could handle molten bronze without turning into a disaster required materials that sound like ingredients for a witch's potion. The foundation of every cannon mold was something called loam, a mixture of clay, sand, and horsehair that had to be mixed with the precision of a master baker. But here's where things get weird. The horsehair wasn't optional decoration. Those individual strands acted like tiny reinforcement bars, preventing the clay from cracking when it got hit with metal hot enough to melt copper pennies. Some foundries swore by specific horses, claiming that stallion hair worked better than mare hair. Whether this was actually true or just medieval superstition probably depended on which foundry master you asked after he'd had a few drinks. The process started with building what looked like the world's most important sandcastle. Workers would create a rough cannon shape using this loam mixture, but getting the proportions right required mathematical skills that would impress modern engineers. The wall thickness had to be perfect. Too thin and the mold would crack under pressure. Too thick and the bronze wouldn't flow properly. Medieval foundry masters were basically doing structural engineering calculations in their heads while working with materials that behaved differently every single time. Here's something that sounds insane, but was absolutely critical. The mold had to breathe. As the molten bronze poured in, it displaced air and created gases that needed somewhere to go. If those gases got trapped, they'd create weak spots in the finished cannon, or worse, cause the mold to explode like a medieval pressure cooker. Workers carefully built in air channels and vents throughout the mold, creating a network of escape routes that had to be positioned with surgical precision. The core construction was where things got really tricky. Remember, cannons need to be hollow. That's kind of the whole point. Creating that hollow space required building a separate core piece that would sit inside the outer mold, leaving just enough space between them for the bronze walls. This core had to be perfectly centered and strong enough not to shift when liquid metal started flowing around it. Getting this wrong meant ending up with a cannon that had walls of different thicknesses, which was basically a recipe for spectacular and deadly failure. Supporting this core required something called chaplets, small metal spacers that held everything in the right position. These tiny pieces had to be made from the same alloy as the cannon itself, so they'd melt and become part of the final product. But here's the catch. If you used too many chaplets, they'd create weak spots. Too few, and the core might shift during pouring. It was like performing surgery while blindfolded. You messed up. The trunnion molds were another, except the patient was a weapon that could kill dozens of people if stubby cylindrical projections that allow can headache entirely. Trunnions are those ions to pivot up and down for aiming. They had to be perfectly aligned and strong enough to support the entire weight of the cannon during firing. The molds for these parts were separate pieces that got attached to the main mold with wooden pegs and sealed with clay. One poorly attached trunnion mold could ruin the entire casting, leaving you with a cannon that couldn't be mounted properly. Drying the completed mold was perhaps the most nerve-wracking part of the entire process. The whole thing had to be heated gradually over several days to drive out every bit of moisture. Any water left in the mold would instantly turn to steam when it hit the molten bronze, creating pressure that could blow the whole thing apart. Medieval foundry workers became expert meteorologists, tracking humidity levels and adjusting their drying schedules based on weather conditions. An unexpected rainstorm could delay a casting by weeks. The mold inspection process would make modern quality control specialists proud. Every inch had to be checked for cracks, weak spots, or imperfections. Workers used special tools to tap different sections, listening for the sound that indicated proper density and strength. They'd shine torches into the hollow spaces, looking for any debris or irregularities that could cause problems during pouring. Finding a problem at this stage meant either starting over completely or attempting repairs that were almost as risky as the original construction. Temperature control during drying was another art form entirely. Too much heat too fast would cause the clay to crack. Too little heat meant moisture would remain trapped inside. Foundry masters developed elaborate heating systems using carefully positioned fires and channels that distributed warmth evenly throughout the mold. Some foundries built special drying chambers that could accommodate multiple cannon molds at once, creating production lines that would have impressed Henry Ford. The final preparation step involved coating the inside of the mold with a special mixture designed to give the finished cannon a smooth surface. This coating, made from powdered charcoal and other secret ingredients, also helped prevent the bronze from sticking to the mold during cooling. Getting this coating applied evenly required tools that looked like medieval paintbrushes, except they were designed to work inside narrow curved spaces while wearing thick leather gloves to protect against heat. By the time a mold was ready for pouring, it represented weeks of careful work by multiple specialists. The investment in time and materials was enormous, and the risk of total failure remained high right up until the moment the bronze hardened. But when everything went right, when the stars aligned and every variable fell into place perfectly, the result was a weapon that could reshape battlefields and topple kingdoms. The moment of truth was about to arrive. Time to find out if all this careful preparation would create a cannon or an expensive disaster. The pour itself was like watching controlled chaos unfold in slow motion. Picture 20 sweaty foundry workers moving around a furnace hot enough to melt your eyebrows off, each one knowing that a single mistake could turn the whole operation into a medieval disaster movie. The furnace had been burning for hours, consuming enough charcoal to heat a small village, and now came the moment that separated master founders from guys who found new careers really quickly. Tapping the furnace was the point of no return. A master founder would use a long iron bar to punch through the clay plug that kept the molten bronze contained. The first drops of liquid metal would hiss and spark as they hit the air, glowing like fallen stars. But here's what made this terrifying. Once you started the pour, you couldn't stop. That bronze was coming out whether you were ready or not, and it was coming out fast. The runners and risers were the unsung heroes of this whole operation. These were channels carved into the mold that guided the flowing bronze exactly where it needed to go. Think of them as the plumbing system for liquid metal. The main runner carried the bronze from the furnace to the mold, while smaller channels distributed it evenly throughout the cannon shape. Getting these pathways wrong was like trying to fill a swimming pool through a garden hose, except the garden hose was made of clay and the swimming pool was shaped like a cannon. Risers served a completely different purpose that sounds counterintuitive until you understand the physics. These were vertical channels that allowed excess bronze to rise up and out of the mold. Why would you want to waste precious metal? Because bronze shrinks as it cools, and without those risers feeding extra metal back down into the cooling cannon, you'd end up with weak spots and air bubbles. It was like having a bronze insurance policy built right into the casting process. The sound alone would have been incredible. Imagine the roar of a waterfall, except instead of water, it's liquid metal hitting clay at temperatures that would vaporize wood instantly. Steam would hiss and billow as any remaining moisture in the mold met the bronze. Workers had to stay close enough to monitor the pour, but far enough away not to get splashed by metal that could melt through leather boots in seconds. Timing the pour required skills that bordered on supernatural. Pour too fast, and the bronze would create turbulence that trapped air bubbles in the metal. Too slow, and the metal would start cooling and solidifying before the mold was completely filled. Master founders could judge the perfect flow rate by watching the color of the molten bronze as it moved through the runners. Different shades of orange and yellow told them whether the metal was flowing properly or starting to cool too quickly. But here's what made this process truly nerve-wracking. You couldn't see what was happening inside the mold. The entire casting was hidden under layers of clay and loam. Workers had to judge success or failure based on external clues: the sound of the metal flowing, the behavior of gases escaping through vents, and the way steam rose from different parts of the mold. It was like performing surgery while wearing a blindfold and oven mitts. The cooling process was where patience became a virtue and impatience became a disaster. Modern foundries might use controlled cooling chambers, but medieval cannon makers had to rely on time and prayer. The bronze had to cool slowly and evenly, or internal stresses would create cracks that could turn a beautiful cannon into expensive scrap metal. Some castings were left undisturbed for up to 2 weeks, with workers posting guards to make sure nobody got curious and tried to peek inside early. During cooling, the bronze went through different phases that changed its internal structure. Too much heat for too long, and the metal would become brittle. Cool too quickly, and stress fractures would spider web through the walls. Medieval founders didn't understand the metallurgical science behind these changes, but they'd figured out through generations of trial and error exactly how long to wait before breaking open their molds. The breakout was like Christmas morning, except instead of wrapping paper, you were destroying weeks of careful mold construction to see if your cannon was a masterpiece or a very expensive lesson in humility. Workers would carefully chip away the outer layers of dried clay, revealing the bronze surface underneath. The first glimpse of metal told experienced founders almost everything they needed to know about the casting's success. A good casting had a smooth, even surface with a consistent bronze color. Rough patches, discoloration, or obvious defects meant problems that might or might not be fixable. The worst-case scenario was finding cracks that ran deep into the metal. Those cannons were destined for the scrap heap, no matter how much time and money had been invested in creating them. But even a perfect-looking exterior didn't guarantee success. The real test came when the cannon went to the boring bench, where the internal bore would be cut to exact specifications. This was where hidden flaws, air bubbles, and uneven metal thickness would reveal themselves. More than one beautiful-looking cannon turned out to have internal defects that made it unusable. The boring process was precision engineering that would impress modern machinists. A long, sharp cutting bar was rotated through the cannon's interior, slowly removing material until the bore was perfectly round and exactly the right diameter. This wasn't a quick job. Boring a single cannon could take several days of careful work. The cutting bar had to be perfectly aligned, or the finished bore would be crooked, making the cannon wildly inaccurate and potentially dangerous to its own crew. Trunnions required their own specialized attention. These mounting points had to be perfectly round and precisely positioned, or the cannon couldn't be mounted properly on its carriage. Workers used files and grinding stones to true up the trunnions, checking their work constantly with measuring tools that were accurate to fractions of an inch. One poorly finished trunnion could make an otherwise perfect cannon impossible to aim properly. The touch hole was drilled last, and it had to be positioned with mathematical precision. Too high, and the powder charge wouldn't ignite properly. Too low, and burning powder would erode the hole over time. The diameter had to be exact. Too small, and ignition would be unreliable. Too large, and gas pressure would escape instead of propelling the cannonball. Medieval cannon makers figured out these specifications through decades of experimentation, creating weapons that were surprisingly sophisticated for their time. Chasing the seams was the final finishing step, where workers carefully filed away any visible lines or imperfections left from the casting process. This wasn't just cosmetic. Rough surfaces could concentrate stress during firing, creating weak points that could lead to catastrophic failure. A properly finished cannon should look like it was carved from a single piece of bronze, with no visible evidence of how it was actually made. Quality control in medieval foundries was literally a matter of life and death. Every cannon had to be proof-tested before it could be delivered to military customers. This meant loading it with a charge of gunpowder and actually firing it several times to make sure it wouldn't explode when soldiers tried to use it. Some cannons failed these tests spectacularly, providing expensive lessons about metallurgy that foundry masters would remember for the rest of their careers. The mathematics behind successful cannon casting were more complex than most people realize. Founders had to calculate metal shrinkage rates, cooling times, wall thickness requirements, and dozens of other variables that affected the final product. They did all this without modern measuring instruments or computer models, relying instead on formulas passed down through generations of craftsmen who'd learned through expensive trial and error. But creating the cannon was only half the story. A bronze tube, no matter how perfectly cast and finished, was useless without the right gunpowder and ammunition to make it deadly effective. The gunpowder situation was where medieval military technology got really interesting. And by interesting, I mean explosively complicated. You couldn't just walk down to the local hardware store and pick up a bag of black powder. Every batch had to be mixed from scratch using ingredients that were harder to find than honest tax collectors in the 1400s. The basic recipe sounds simple enough: saltpeter, charcoal, and sulfur in specific proportions. But getting those proportions right was the difference between a cannon that could knock down castle walls and one that fizzled like a wet firecracker. Saltpeter was the real headache ingredient. This stuff had to be mined from caves, where bat droppings had been aging like fine wine for decades, or scraped from the walls of old cellars, where it formed naturally through a process that medieval chemists understood about, as well as modern teenagers understand rotary phones. The best saltpeter came from India, which meant European cannon makers were dependent on trade routes that could be disrupted by wars, storms, or pirates who probably had no idea they were messing with military supply chains. Here's something that sounds crazy, but was absolutely true. Some kingdoms actually had official saltpeter men whose job was to dig through people's barnyards and cellars, looking for the white crystals that formed in soil rich with animal waste. Imagine being the guy who had to knock on doors and say, "Excuse me, mind if I dig around in your manure pile? It's for national defense." Talk about a job that required excellent people skills and a strong stomach. The charcoal for gunpowder wasn't the same stuff used for melting bronze. Cannon founders needed charcoal that burned hot and steady, but powder makers needed charcoal that burned fast and completely. This meant using different types of wood processed in completely different ways. Willow and alder were preferred because they produced charcoal with exactly the right density and burning characteristics. Getting this wrong could mean powder that burned too slowly to build up pressure, or too quickly and blew up in the barrel before the cannonball had time to move. Sulfur was easier to source, but harder to purify. Raw sulfur often contained impurities that could make gunpowder unreliable or downright dangerous. Medieval powder makers became experts at refining sulfur through distillation processes that involved heating it until it vaporized, then capturing the pure sulfur as it condensed back to solid form. The whole process smelled like someone had opened a gateway to hell in your backyard, which probably explains why powder mills were usually built far away from populated areas. But mixing these three ingredients together was just the beginning of the powder-making process. Early gunpowder was made as meal powder, basically grinding everything together until you had a fine grey dust that looked harmless enough, but packed more explosive power than medieval people had ever seen before. The problem with meal powder was that it separated during transport. The heavier saltpeter would settle to the bottom, while the lighter charcoal floated to the top, creating powder that burned unpredictably. The solution was something called corning, which sounds like it has something to do with vegetables, but was actually a process of turning meal powder into small, uniform granules. This involved mixing the powder with water or wine. Yes, wine was sometimes used because medieval powder makers believed alcohol improved the burning characteristics, then pressing it into cakes and breaking those cakes into granules of specific sizes. Different sized granules burned at different rates, which meant powder makers could customize their product for specific weapons. Fine powder for small firearms, medium granules for cannons, and coarse powder for the biggest siege guns. Getting the granulation right required experience that could only be gained through years of practice and probably more than a few accidental explosions that sent apprentices looking for safer careers. The quality control process for gunpowder was both primitive and terrifying by modern standards. Powder makers would test small samples by lighting them on metal plates and judging the quality by the color of the flame, the speed of burning, and the amount of residue left behind. Good powder burned with a bright flash and left minimal ash. Poor powder sputtered, smoked, and left behind chunks of unburned material that could clog cannon touch holes. From molten bronze to thundering bombardment, we've traced the incredible journey that transformed raw copper and tin into weapons that reshuffled the medieval world. Every step, from the sweating foundry workers mixing precise alloy ratios to the master gunners calculating powder charges, required skills that would impress modern engineers. These weren't just metal tubes, they were the product of supply chains spanning continents, mathematical precision that bordered on wizardry, and craftsmanship passed down through generations of specialists who literally bet their lives on getting every detail perfect. The next time you see a castle wall, or read about some medieval siege, remember the army of metallurgists, powder makers, and gunners whose expertise made those crumbling stones possible. Subscribe for more deep dives into the technology that changed history.